Welcome back to Wickerson Studios. There really isn't any beating around the bush with this. I have gone so, introductory deep into the beginnings of calculus. I have jumped into functions full out. I'll be doing inverse functions, limits, continuity, and moving into differentiation and then the higher order derivatives very soon. But this is the second major script coming out of this series. Started with what is calculus in the last one, dealing with the Cartesian plane and graphing and things like that. But where I ended my last video was pretty simple. I started to tuck a lot of these things into GH Python and C# nodes, and that's what I'm intending to do with this series. I'll probably make plugins that actually make these fairly simple. Now, most of these tools are already in the math node if you know how to run them and how to build things, but I'll make them pretty compact and efficient. So what I did was I jumped in and I said, okay, let's take a look at let's get into the squares of numbers that cannot be negative from the square roots. We started graphing things like that. I started graphing y at square root of x. Then I started to set up its domain limits as I went. More complicated functions have more drawbacks for having to map them out, so you want something that can really work those fairly well. I have my basic graph that I keep introducing here, which should be tucked in here somewhere if I selected it. Don't see it. This was just a working domain set. So I actually started thinking about, okay, what happens when we start to add functions together? How do the domains react to one another? And I noticed Grasshopper had a lot of these really nice set tools for finding out if you had two different domains, you could kind of go in and play around. So I started playing a little bit within that, but it's really not something in the set tools that I'm too interested in delving into a little bit more. I think I'll stay with the math and calculus out of this text. And then I started to graph what happens when you start to add these together, when you multiply them together, when you start to tuck them and nest them into one another. You end up getting these wonderful graphs as we go. All of these have been labeled. There's lots of points within here of what's happening on each one. And keeping the graphs fairly simple, but really focusing in on what does it mean to graph something, a domain within a domain, and where are your limits to what can happen? When do things start and stop? So I'm not going to go into full detail here. Obviously, there's a ton of information playing off of dividing, setting up the fact that even though this may look like the function h at x equals x, there is this kind of point where it disappears within this function, and you have to set up multiple domains. And that's exactly what I do. And whenever there's multiple domains that I have to deal with, well, it's really a domain, but it has a break within it. You can say this one looks like a straight line, but there actually is this point here where this line ceases to be and this line ceases to be as they meet together. And you can kind of slide around in here and have a lot of manipulation on where that is to read that line. That's actually setting the, if you see this little h at x at a at x, basically there's a multiplier and it only can go up to that point and then it stops. And then the other script, which is down here, kind of takes over from that. If we zoom in, and you should be able to, after doing this, see how that jumps all the way down and stops at that point, right before it becomes it. Then I talked about odd and even functions, wrote a little bit out of the text of what that means, and how it means symmetry within your function, how you read. Then I did a ton of exercises, exercise after exercise after exercise after exercise. Very simple ones to start, more complex as we went. Whenever I saw constant letters, I started to add in the b variable. So you'll see here, as I add in the b variable, I have this ability to jump in here and affect a and b. So they're pretty parametric models as they go. And also, they're just for the purpose of producing beautiful, wonderful curves, which then can be taken very quickly off in your perspective window, lofted and turned around, and think of the millions and billions of geometries that come out of these simple math functions. And once you gain parametric computational control over these, things will be good. Now, whenever I had to use what I call multiple domains, a sense of where something starts and stops, you'll see that this one defaults. There's no other way around it. As I put in the range, like I'm saying, it goes up to less than -2. So this looks like it faults out because it divides by 0 if it becomes 2, but it still runs the rest of the script. So you end up finding within here, if we take a look in this one, you end up finding the asymptotes of that, which is a very nice one. Let me just turn that off, and there you go. You can see where it runs up this way and up this way. Maybe we'll go back to top view just so we can see what's going on within that these never meet because there's an asymptote between where they can't actually meet. So there's a lot of complexity in here as we go, but then I get into these what I call multiple domains in the sense like, I should say multiple curves on the one domain. They separate. And there's probably a better math term for that. So there's another interesting one here that I think I have defaulted, and I'm not sure why. Let's take enable, and know what has happened with that one. That one might have faulted out on me completely. No, I've got lots of data there. I just have to find out where it is, why it's not coming up. Maybe my preview was off. Preview on. Preview on. Yeah, we do have a little something in there tucked away. And what is that one really doing? Let me grab all my visuals here down to here and just hit preview on. And there we go. Same type of asymptote play that I have going on. You can affect one and the other. Sometimes B is still hooked up, but I'm not running it into the equation. But you certainly can amplify and change these if you want. And of course, you're affecting one side of it while you don't affect the other, which gives you pretty good geometric control if you think about product design, sculpture, and everything you might make with it. The scripts are pretty basic, but it's good to adjust your eyes to when you see the square root of something similar to this, or divided, or 1 divided. It's going to get a little trickier as we get into inverse functions as well. And then I start doing some strange things. I start to take a look through here and saying, okay, where do things kind of funk out? I use this basic tool of writing the script in a node-based script so I can slide through the full range of my domain and check if there's a square root. If there's a square in here at any time this becomes negative, that's going to tell me there's some problems with that script. So I'm just going to leave that one and see what happens. It becomes more and more fancy as you get into here. And what's exciting about the single domains as we go into here, we're going to start being warned by a very interesting fact here as we go through. This one should behave all the way across. It holds at 3. So this is a nice little graph here that you actually have this pretty hard bounce as to what happens within this one. But here, you got to watch out for these complex numbers. Take a look at this little test of the script. If you're going to run something as simple as this, 4 minus the square root of that number within a certain domain, and then find the square root of that, the square of that, square root of that. Take a look at this. Everything behaves well between 2 and negative 2. It's a single number, but all of a sudden, bang, we jump into a set over here of I and J, which means we're starting to deal with complex numbers. And if you haven't figured out complex numbers, you're going to have a little bit of trouble trying to perceive and conceive of what that means to a graph when you're actually dealing in that range. But basically, we're just dealing with the top half of the circle. Not that hard. So I know this looks incredibly complex, but it's actually incredibly easy when you get into it. Let's just play around a couple of sets, see what we can pull out of this one. Still have some nice, and let's just do that little amplification on the A, which just pushes it up and down, which isn't too exciting. There is a B within here, which is kind of fun as I flatten it out, and you can take it through instead of integers. You don't have to set it to integers if you like. But you see that it does bounce at certain points and say, no, you're going to have an area that you have to be careful of in here that it just doesn't work for as you get into those complex numbers and move outside of that that negative 2 to 2 range. I think it's still negative 2 to 2 range in this scenario. Then you got some absolutes you can play with. Absolute square roots, all these things, inverses are going to be really exciting. Finish that off. Lots of examples brought out of a textbook. Just a few pages of a calculus textbook, and you can produce an incredible tool like this that if I was kind to people within Grasshopper, I'd probably start nestling all these into really nice scripted, optimized C nodes or Python nodes and give them a nice little icon and slip them into the math nodes so I can have completely parametric control when I start to want to say grab this curve and this curve and simply start utilizing the Z direction. So I'll just try and do this for you right here. We haven't done anything in the Z. So if we grabbed a loft in the Z, which we're going to bounce out of this in a second. If I hit this, I'm going to have to go back in and highlight it. Let me grab a Z right here, 4. It shouldn't hurt. Let's just grab part of our range and throw it directly into that Z. And there you go. You've got a nice little effect of that, but maybe even more so, I should just grab it into the Z and throw it up in that direction like that. 2 nice little curves. Still trying to follow with some of my images. And that should give us, let me see, this curve and this curve. If I'm wise to it, this curve and this curve. So we should be able to very quickly grab a loft. And let's grab one of these curves out of here. Of course, when you go to Grasshopper, you don't even have to see what the nodes are. And we'll take that set there and throw that in. And there we go. Nice little loft between their little surface that's made from a little bit of math. Fully parametric curtain wall. Really nice if you start thinking about the subtleties of this and what it may mean for you as a sculptor or an artist. And certainly throw in some nice parametric control as we're going in one direction and the others. Be careful of your Yeah, where it explodes out and behaves kind of nastily. That's an interesting form there. I think what I'll do is just grab that loft and throw it into a little bake. And there you go. You made a pretty cool shape that under a beautiful surface analysis, that could be pretty nice. Let's grab that as a surface zebra analysis, see what's going on. There you go. Pretty nice and psychedelic wall nosing out beautifully. Nothing too hard about something like that, but just a little playfulness. Whenever I do something a little tricky like that in my script, I usually slip it into a little tiny group and warn myself that Wickerson was having a little bit of fun here, a little bit too much fun. Getting away from the script. So that blue indicates that Michael's kind of playing off of some geometries. And the potential for playing off geometries of these scripts is just amazing. And if you don't believe beauty comes from math, play around with some of these curves computationally and prove it to yourself. So there we go. Section 2, and we're going to go into Section 3. We're going to crawl through this calculus book and start applying it to all the beautiful things in the world that you could be making. Thanks for